We have all been watching the wrong scoreboard. For the last 2 years, the global AI conversation has been obsessed with the absolute frontier. We continue looking for the highest parameter counts and the top scores on abstract reasoning benchmarks. We focus on the $100 billion supercomputers being built in the middle of the desert. But while we were all staring at the absolute ceiling of artificial intelligence, a different shockwave has been quietly building at the floor. This chart shows the friction in the current market. The frontier is expensive, yet the businesses and developers trying to use this technology cannot afford to pay those luxury prices at scale. When the cost to use a model exceeds the value created, the technology remains a prototype. For most of the world, the barrier to AI adoption isn't what the models can do, it's what they cost to run. Consider the monthly API bills for a mid-sized company trying to integrate a top-tier model. Look at the staggering compute costs required to run a massive reasoning engine for millions of daily queries. For widespread, invisible integration, these numbers are currently impossible to reconcile. The optimized systems emerging now are doing more than just writing polite emails. These systems rely on radical cost efficiency and the compression of the frontier battlefield. In this environment, the competitive advantage is no longer just being the smartest model in the room. The advantage is being strong enough while becoming cheap, accessible, and fast. The AI race is moving away from the pursuit of maximum size. We are seeing a shift toward making high-level intelligence inexpensive enough to spread everywhere. We aren't going to walk through a history lesson about the industry, and we aren't going to hide behind a keyword soup of technical jargon. Instead, this is a usable map of how model efficiency is changing the costs of the industry. We will look at how the compression of capabilities changes who gets to build on artificial intelligence. We'll see why the old luxury moat of having this single biggest model is starting to crack. We'll explore what happens when frontier-level performance becomes a cheap commodity rather than an expensive privilege. This is about the economics of intelligence. A rising floor is much more disruptive than a breaking ceiling. To find where the leverage will be in the next 12 months, stop looking at the benchmarks and start looking at the bills developers are paying. For years, the artificial intelligence industry operated on a single assumption. Scale was the only thing that mattered. The thesis was simple. If you pump more data and computing power into a neural network, it inevitably gets smarter, and the smartest model captures the entire market. This belief kicked off a massive arms race. Companies started spending billions to build the most expensive supercomputers on the planet, all to train models with hundreds of billions, sometimes trillions, of parameters. Look at this dense array of server racks and miles of cabling. This is the hardware footprint required to turn that strategy into physical reality. And for a while, the strategy worked. The biggest models were undeniably the most capable. If developers wanted to build a serious application, they had to pay premium prices. But this arms race created a brittle ecosystem. By tying artificial intelligence exclusively to astronomical, centralized pools of capital, the industry set a trap for both the creators training the models and the everyday consumers trying to use them. The physics of economics eventually caught up with the ambition of the researchers. While tech giants were building megaclusters, a normal startup or enterprise was just trying to integrate these models into their workflows. This chart illustrates the core problem: variable costs. Every single time a user interacts with a massive frontier model, it invokes a huge amount of computing power. If you're building a customer service tool, your computational costs scale linearly with your usage. The smarter the model, the more expensive it is to run. Having a system that can pass the bar exam is impressive, but businesses don't actually need a lawyer to summarize a daily meeting transcript. Businesses quickly ran the numbers. They realized they don't need peak intellect for everyday tasks. They need systems that are fast, systems that are highly reliable, and incredibly cheap to operate. That variable cost bottleneck triggered the second phase of the artificial intelligence race, a pivot toward extreme efficiency. Engineers realized they could train a smaller model to perfectly execute specialized tasks. Through a method called distillation, they bypassed the need to invoke a massive behemoth for every prompt. Through targeted architectural improvements and quantization, these specialized models began achieving performance levels that the compression of the frontier. The massive infrastructure requirements from just a year ago are rapidly shrinking. This is the kind of immense, towering data center aisle we used to need just to run high-level reasoning tasks.
Today, those exact same capabilities can be packaged and run on a dramatically smaller hardware cluster. The compression is so severe that advanced models are now capable of running entirely locally on high-end consumer devices, without pinging a server at all. By shrinking the physical footprint of these systems, the technology democratizes access. Developers are severing their reliance on centralized, expensive cloud infrastructure. When frontier-level performance becomes highly compressed, the economic leverage shifts. The companies that figure out how to offer strong capability at ultra-low costs suddenly hold the market leverage. This scale illustrates the mathematical threshold. At 10 cents per query, innovation is blocked by cost. But as the price drops to a fraction of a cent, we're suddenly looking at entirely new markets that become profitable at this lower price point. We're talking about billions of microtransactions, automated background tasks, and deep embedded system integrations. Older systems relied on expensive individual queries from a user. High-efficiency models instead handle thousands of automated processes in the background of an application without direct supervision. Aggressive price reduction doesn't just cheapen current tools, it births entirely new economies that run constantly in the background of our software. This graphic shows the new global strategy. Companies are ignoring absolute peak benchmark scores and targeting the cost-performance ratio. If you offer developers a model that is 80% as capable as the absolute best, but it costs 1/50th of the price and runs 10 times faster, you bypass the massive, slow giants. This new equation rewrites what software can be built. The core competitive metric is no longer raw intellect. You stop competing on who has the smartest individual model, and you start competing purely on distribution and scale. The luxury moat of having the smartest model is breached, not by a smarter model, but by a tidal wave of perfectly adequate, aggressively cheap intelligence that floods the market and becomes impossible for developers to ignore. We have to pressure test this entire thesis. In a technology market moving this aggressively, locking into sweeping conclusions is a great way to get blindsided. The primary counterargument to the cost efficiency narrative goes like this. The absolute frontier of artificial intelligence is going to advance so violently that smaller, cheaper models will be rendered entirely obsolete. Skeptics point toward artificial general intelligence, a hypothetical system with the capacity to execute massive, multi-step autonomous reasoning without needing a human to guide the process. Imagine a model that can autonomously invent a novel chemical compound for a new drug, or write a complete software operating system from scratch overnight. The economic value generated by that level of output is staggering. Look at this scale comparison. If a system generates trillions of dollars in fresh value through autonomous action, the API cost to run that specific query shrinks to a simple rounding error in the grand scheme of business expenses. This is a perfectly valid boundary condition. If the capability ceiling rockets upward and makes autonomous agents viable, the cost efficiency argument takes a back seat. But we have to separate a hypothetical future trajectory from our immediate economic reality. Assuming the rules of tomorrow apply to the market of today is a costly miscalculation. The reality right now is that the vast majority of enterprise and consumer applications do not need an AI to invent a revolutionary pharmaceutical drug. They need a model to format unstructured data. They need it to answer routine customer service questions, categorize text inputs, and generate basic boilerplate code. For those specific everyday tasks, the capability ceiling has largely been reached. Existing models are perfectly capable of doing the job. This chart tracks exactly what happens next. Notice the capability trend line. Because the models are already good enough for everyday use, the trend plateaus, leaving only two meaningful vectors for market competition: how cheap and how fast the models can run. For the bulk of the market, paying a premium price for a frontier model's deep reasoning to execute a basic sorting task is a wasted business expense. However, we have to be highly precise about what model compression actually achieves. It is an exaggeration to claim that cheap, optimized models are ready to replace frontier models across every single domain. They are not. Smaller models still stumble when you ask them to perform deep, multi-step logic. They struggle with complex mathematical problem solving, and they easily lose coherence when forced to maintain massive context windows. If you deploy a highly compressed model for a task that requires absolute zero margin of error execution, you will watch it fail spectacularly. This visualization maps out the true impact of the efficiency shock. The addressable market for the largest AI models is not disappearing. Instead, look at how it retracts strictly to high-stakes tasks that require massive computational weight. The heaviest computational models remain essential. Their identity has simply shifted from universal, everyday tools into highly specific, specialized instruments. So what decides the final balance of power? It comes down to a race between two speeds: the rate of bottom-up commoditization versus the rate of frontier breakthrough. Imagine a scenario over the next 2 years where the absolute best frontier models manage only incremental, slow improvements. Cost efficiency players will consume the broad market from the bottom up. Developers will rapidly migrate workloads to cheaper alternatives. The only thing preserving premium pricing is a discontinuous leap, a massive architectural breakthrough in reasoning. But until that massive leap actually occurs, the inescapable gravitational pull of the market is dragging all everyday applications toward the cheapest possible floor. The companies currently prioritizing radical cost efficiency are building the structural foundation that will power the next generation of deployed software. Meanwhile, the frontier companies run a very specific risk by pushing absolute limits of capability without aggressively driving down costs. They could end up building luxury engines that are simply too expensive for any broad market developer to actually drive. This relentless drive toward efficiency forces a complete reevaluation of how we measure progress in artificial intelligence. Future economic dominance depends on effective deployment within strict constraints, which carries more weight than the total volume of data a company can hoard. As these ripple effects reshape global technology investments, adaptability will be the defining characteristic of success in this new landscape.
Navigating the current artificial intelligence landscape requires a specific analytical map to separate laboratory metrics from commercial results. The industry operates across two distinct layers: the research frontier and the deployment reality. The research frontier is defined by parameter counts and reasoning benchmarks measured in a vacuum. But the deployment reality is governed by variable costs, latency constraints, and developer adoption. Strategic failure occurs when the rules of the frontier are applied to the logistics of deployment. The current efficiency shock proves that laboratory success does not guarantee a viable product. This theoretical divide is currently playing out across a chaotic market efficiency shock. Many market strategies are built on the assumption that winning at the research frontier leads to automatic dominance in the deployment reality. In the real world, massive models face a profitability wall. Maintaining profit margins is difficult when the compute costs on a single query outweigh the value of the task being performed. The requirements for a lab experiment and a scalable enterprise tool have completely diverged. A high reasoning benchmark provides no commercial advantage if the resulting system is too expensive to be integrated into a standard business workflow. For developers, investors, and business leaders, this shift requires a new operational framework. The focus is moving away from the question of which model is the absolute smartest. The priority is now identifying the model that provides the exact level of intelligence required for a task at the absolute lowest cost. Intelligence is becoming an industrial utility. It is a raw resource with a measurable price point and a specific performance envelope. You do not use highly refined aviation fuel to power a lawnmower. Similarly, using a trillion-parameter frontier model to sort an email inbox or format a spreadsheet is an engineering mismatch. Treated as a variable cost utility, the focus shifts from maximum capability to infrastructure efficiency. Internal architectures are shifting toward a strategy of aggressive workload segmentation. Simple, high-volume tasks are routed to incredibly cheap, optimized models specializing in speed and cost efficiency. Massive, expensive frontier models are reserved exclusively for rare tasks demanding deep, multi-step reasoning. The cost differential between these pipelines is orders of magnitude apart. Mastering this segmentation allows an organization to achieve 90% of the capability of a frontier model for 1% of the cost. Looking at the major technology giants, the defensive positions they built around massive, monolithic models are beginning to erode. The era of the one-size-fits-all luxury AI model is ending.
The industry is moving into a period of severe fragmentation, where intelligence is rapidly commoditized. The defensive moats surrounding leading AI companies are proving to be much shallower than expected. Competitive advantage is shifting toward proprietary data, the user experience, and the specific workflow integrations that surround the model. When intelligence becomes cheap and ubiquitous, the core model itself loses its premium. Companies must now compete on the quality of the infrastructure built around that commodity. The industry is engaged in a grueling marathon to build the most efficient engine for the real world. Radical accessibility is becoming the primary driver of market share, as the scale of adoption is dictated by the cost of the entry point. Conquering the market requires a tool that is simultaneously good enough to solve the problem and cheap enough to scale indefinitely. Thank you for watching The Intelligence Shock. If you want to survive the absolute chaos of the next technological cycle, you have to stop following the mainstream hype and start tracking the cold, hard economics. Hit the subscribe button to join our strategic briefing, because when the frontier eventually collapses into a cheap commodity, we are the ones who will show you exactly how to navigate the wreckage and profit from the fallout. See you in the next analysis.